If we're going to be working with transfer functions, we'll see a lot of block diagrams. Block diagrams are a visual way of representing an entire system. And there are three common forms that you'll see in block diagrams that can be reduced to a simpler form. The first is cascade form, where we have one transfer function after another. So here we have the input R and the output C, and the intermediate steps we have x2 and x1. And so whenever we talk about reducing these to an equivalent form, we just mean algebraically equivalent. So here we have R times G1, and then that times G2, and then that times G3 gives us C of S. So that's equivalent to just combining these three block transfer functions into one, which is the product of all of them. So R times this is equal to the same thing as this. Parallel form can be reduced, and again, when we talk about reducing it, it's just algebraically equivalent. So here we have a pickoff point, and the signal R is multiplied by three different transfer functions, and those products are then added at a summing junction. And this form here is equivalent to one transfer function that's the sum of the three individual ones. And note the plus minus, the signs stay the same. So if they're all added in the summing junction, then they're all added, or if any one of them is subtracted in the summing junction, then it's subtracted here in this sum. And finally, we have feedback form. This shows one general or common way of implementing feedback. So we'll have the input and then the input transducer that goes to a controller or compensator, and then that finally goes to the plant or the system that we're controlling. The output of the plant is then fed back, possibly through an output transducer and feedback, to a summing junction. In a more general term, we have the input, the feed forward transfer function, G of S, and then feedback gain, H of S. And this system is equivalent to this transfer function. So we have G of S over 1 plus G H of S. Or it's really plus minus, and note that the signs here are inverted. So if this summing junction is R minus H times C, then the denominator here is going to be 1 plus GH. If this is R plus H times C, then this is going to be 1 minus G times H. In order to reduce block diagrams to simpler forms, we can rearrange them and get those common forms, those three common forms that we saw before, reduce those to their equivalent transfer functions. In order to massage block diagrams to get them to have those common forms, we need to sometimes move blocks through either summing junctions or pickoff points. So let's see what's the equivalent of moving a block through a summing junction. And again, we're talking about algebraically equivalent. So here we have C of S is equal to the sum of R and X times G. So if we wanted to move this block before the summing junction, then we need an algebraically equivalent system. And so that looks like this. Now C of S is equal to R times G plus X times G, which is the sum of R and X times G. So that's one way of doing it. The other way is if we wanted to move the block after it. Here we have R of S, or excuse me, C is equal to R times G plus X. So if we wanted to move the block after here, after the summing junction, or on the other side of the summing junction, then we need to have an algebraically equivalent system. So now we have, again, C is equal to R times G plus X, because the G's would cancel out. And then if we want to move the block through pickoff points, we can either move it from one branch to before the pickoff point, and we need an algebraically equivalent system. So we have the same signals on these three lines in either case. So here we have R times G, R, and R. And if we wanted to move G before the pickoff point, well, in the top one we've got R times G, and then we need 1 over G in order to cancel it, so that we still have the R's on the other two. And if we want to move it after the pickoff point, then we just need to duplicate G to all these lines so that the signals on those lines are equivalent to what they were before we moved the transfer function or the block. And now we'll look at using these things that we've learned in an example where we want to simplify this block diagram. So here's a block diagram for our system, and one could come up with a block diagram like this just from looking at how the subsystems are interconnected. But this is sort of unwieldy to work with, so we want to reduce this to a simpler system, or to a single transfer function. So we use the techniques from the previous two slides to reduce this block diagram to a transfer function. Okay, so the first step, or the steps are, one, we want to look for common forms. And reduce them once they're found. Yeah, we're not loofing for them, we're looking for them. And then two, once we've reduced all the common forms that are possible, then we want to move blocks to get common forms. And once we've gotten those common forms, then once we move the blocks, then we go back and repeat this until we've arrived at one transfer function. So for this example, there are no common forms. There's no cascade, parallel, or feedback forms. We'll start here and try to get a feedback form out of this. So let me just draw that one little part. So we had V2, we had a summing junction, and I'm going to move G2 before this pickoff point. So then we had G2, and then this is V4. So V4 is fed back through H2, and that goes to the summing junction. So over here we have this goes to another summing junction, and so we need the inputs to this summing junction to be the same as in the original diagram. So here we have V3, which is V2 minus V7. But in this example, after we move G2, that's all multiplied by, so this is V3. And we want this to be V3, but right now it's V4. So anyway, we can multiply this by 1 over G2. And now we have, again, V3. So now this is equivalent. And furthermore, we have this feedback form. So this is equivalent to V2. Whoops, this is just a label for the signal. V2, it's not a transfer function. And we have G2 over 1 plus G2H2. And then that goes to the summing junction like we talked about. Okay. And that actually is another common form. So this line here, which is V4, and then this line, so those are added. We can decompose this into two summing junctions, and this one here we can reduce to a parallel form. So we've got V2, G2 over 1 plus G2H2, and then we have 1 plus 1 over G2, and that goes to this summing junction where we had the feedback. And we can reduce that. Okay. So now we've got this feedback form that can be reduced. Ooh, I almost left off this. Right, I should go ahead and draw this so I don't make a mistake. There's also feedback here going to H1. And so that comes here. And the reason it's important that I not leave that off is because it almost looks like we have a cascade form here. If I hadn't put that on, then we could have just multiplied this transfer function by that one. But then we would lose this signal, and that would alter the result of this summing junction. So anyway, I just need to be careful to leave that in. And this, of course, is equivalent to G3 over 1 plus G3H3. So these two can be combined in cascade form. And what we end up with is R goes into the summing junction, and the output of that is multiplied by oops, I left out G1. Excuse me here. So there's G1. So we have G1, and then the output of R, the summing junction times G1 gives us V2, and that was our input here. So now we've got this transfer function, and the output of that is fed back to H1 through H1, and then we have these two, so 1 plus 1 over G2 okay, so here's our equivalent system, and these two we can combine into cascade form. So this gives us G1, G2 over 1 plus G2, H2. And now we have feedback form, and we can reduce this system. And then we'll have that transfer function cascaded with this transfer function. So what we end up with is R times G1, G2 over 1 plus G2, H2 divided by 1 plus G1, G2, H1 and by 1 plus G2, H2. And that's cascaded with and now we take the product of these two and we could simplify them to get a transfer function. And going ahead and reducing that, we get this for the first block. And then we had the second and third blocks. Well, the second block was a cascade. And simplifying this, we end up with our transfer function as shown here. G1, G3 times 1 plus G2 divided by the product of 1 plus G2, H2 plus G1, H1, G2 and 1 plus G3, H3. So we've looked at what a transfer function is used for, common forms of transfer functions and their algebraic equivalents, moving blocks around in transfer functions and their algebraic equivalents, and an example of reducing a somewhat complicated block diagram to the equivalent transfer function.